Okay, good morning. So let us continue the lesson. If you remember, there are three problems I think left from the first session that I didn't have time to discuss about it. But before we can start from that, of course, let me start with one of them. Do you remember? So we had something like this. I cannot exactly produce the same shape, but yeah, that was more or less the same shape. And the good point is that what we want to show is completely independent from very detailed properties of that shape, actually. Yes, something like that. So we had something like this, and then this is called A, B, C, D, E, and F, and finally G. And we are supposed to calculate the sum of these angles. So if you don't mind, let me just denote them by little a, and then this is little b, little c, d, e, f, and g. So I want to see if I can say something specific about the sum of these 7 angles, I suppose. Yes, A, B, C, D, E, F, and G. Yes? So that was one of our problems, actually, that we were supposed to think a little bit about it. Okay, I don't know, have you thought about the problem, and if you have any ideas, we can discuss it together here. Do you have the number?
Yeah.
What's the number?
540.
540, okay. Okay, so I don't know exactly the number I have to calculate, but might be you're right. So how do you proceed?
Well, I drew a line from E to G and E to C, and you can see that it's a star and triangles attached to the sides. So
From E to
G
and
E to C.
And E to C. Okay, and then you make a star shape.
Yes.
That we already know the sum is 180,
Yeah.
and then probably use that one. Yes.
Yeah.
So any other ideas? So might be that's correct. I can probably show your idea to see if it works. So you are saying that, okay, I connected this to that one, and then you also connected this to this one. Then if you momentarily ignore these black parts here, I hope that you can detect a star shape, yes? And then, okay, so what you are probably saying is the angle A plus angle B, but plus this part of the angle, yes, if I can call it alpha, and then plus this part of the angle, if I can call it beta, and then plus what? Plus A, B, C, this one, and that one. This part of the angle, if I can call it gamma. This is 180, am I right?
Yes.
This is the line that you want to go, yes? Of course, this depends on your proof for this star. Yes, okay, so let us assume that we already know that proof, which was, of course, very easy. Okay, then how do you want to proceed then?
Well, we can see that the remaining angles on that, they're both triangles, so we know that both.
Yeah, so here,
Yeah.
leftovers are this part, and that part,
Yes.
which constructs a triangle.
Yes.
Yes? And other leftovers are this part, and exactly that part. That's also a triangle. So if I add those leftovers to this, then I hope that you agree with me that I will get the sum. So I need to add 2 more 180 to this one. Is that understandable? Everyone? Is that understandable? Yes. So what we did, I don't know if you have watched the video, so we showed that this star shape, when I draw it, independent of the size that I do, the sum of these angles is always 180. And we are using that, so he was actually smart enough to see that if he adds these 2 lines, then what will happen? Then we will have a star shape. Yes, this way. Yes, that's a star shape. So we know that the sum of those angles should be 180, and there are some leftovers when it comes to this sum. The leftovers are this part, and that part, and this part, and that part. But the sum of these makes a triangle, so we know the sum is 180. The sum of these also is 180. So when I add them, I exactly get the same thing with 3 180s, so that is 540. So that's completely correct. Any other ideas? Of course, for such a proof, in the exam, probably you have to prove the star shape first, because that's not a very fundamental theorem that you can refer to. So if you want to go along these lines, you have to have the proof of the star shape in the answer, and then say that, okay, I use this property now to prove this. Because this is not like a theorem that you can prove. So, I mean, that's not a theorem that you can just refer to it without mentioning why. Yes, so let me now see what else. So Rasmus, do you want to say something now?
Mm-hmm.
Yes?
We could solve it in a sort of similar way to how you solved the problem of finding angles for a star shape.
Yes, yes.
In that we first find the angles alpha and beta, which I defined as the maybe you can say like the two corners of the protruding extra part. So
Here,
that angle.
this angle.
No, not that one. The one on the opposite side of that small triangle.
So here,
No.
this one.
That one.
Yeah, this one.
Mm-hmm.
Yeah.
Which we'll call beta.
Beta.
And then you can draw alpha on the
Alpha where?
on there.
Yes. Yeah.
And since alpha and beta are exterior angles on the triangles or beta is an exterior angle of AG.
This one.
No, not that one, of AG and the intersection point.
Yeah. So you mean that beta is the exterior angle to this one, yes?
Mm-hmm.
Yes,
Yeah.
that's right. So beta becomes G plus A.
Yeah.
So that's what you are saying. Yes,
Mm-hmm.
is that understandable? So this angle is an exterior angle of this triangle, yes?
Mm.
So then beta is equal to the sum of these two opposite interior angles. So it is A plus G. That is correct. Then?
And then alpha is the sum of B and C, since it's the exterior angle.
So let me see. B and C, yes. So you see here, now consider this triangle. Yes? Alpha is an exterior angle for this triangle again. So alpha should be the sum of B and C. Yes? Of B and C. Yes?
Yeah.
Okay.
And then now we have a pretty simple problem, because now it's just the pentagon of D, E, F, and
These
alpha
two.
and beta.
Yes.
And so we know that D plus E plus F plus alpha plus beta should
Mhm.
be equal to, what is it, 500 and...
So alpha plus beta plus F, let me write the order, D, E, F, are the interior angles of a pentagon, yes? One side, second, third, fourth, and fifth. So that's a pentagon, yes?
Mm-hmm.
And we already know that sum of the internal angles for any n-gon is, I really want you to memorize that. Of course, you understand it and then memorize it. So that's the for the n-gon. So here I have a pentagon, so n is 5. I put it there, it becomes 3. Multiplied by that, it is 540. Okay. Now, do we have some problems?
No.
No?
Now we
Okay.
just substitute alpha, or A plus G and B plus C for
Yeah.
alpha
So
and
instead
beta.
of alpha, I have B plus C. instead of beta, I have a plus g. So then it becomes a plus g plus b plus c plus d plus e plus f. 1, 2, 3, 4, 5, 6, 7. All of them is 540. Yes? So I think both perspectives are actually very good. One of them is that this is also a good thing. You can break the problem into the problem that you have already solved. So what Oscar presented is very good because he actually used one of the problems we had before. Okay, and then this is also very good because we are actually using the fundamental theorems that we don't need to prove them when it comes to the exam, because this exterior angle is the sum of two opposite interior angles is something very famous, and we really don't need to prove it again in the exam. I appreciate both perspectives, so then we see that this is the case. Okay. But before starting the next one, let us take this problem as an excuse to go a little bit deeper. We will not be able to prove these things because they are a little bit more advanced, but I think it's good to know about them. So far, if I ask you to draw a quadrilateral, so usually you draw it in this way. Something like that. I don't know. It might be. It's a little bit a special case. This seems like a trapezoid, but I mean, so you can probably draw something like this. This is a quadrilateral, yes? If I ask you to draw a pentagon, so it might be you draw something like that. 1, 2, 3, 4, and then 5. 1, 2, 3, 4, and 5. So that's a pentagon. But of course, these are called convex shapes. Okay, but what do I mean by convex? A shape is called convex. Let me just, instead of defining it very officially, so let me just tell you what is the difference between a shape which is convex and a shape which is not. For example, this shape is not convex. What does it mean? It means that there are 2 points interior to this shape, for example, this point and that point, so that when I join them, some part of that line segment lies outside the shape, exterior to the shape. So that is called a non-convex, or some people call it concave. Yes? So this is not convex. But if that is not the case, I am facing a convex shape. Yes? So here, do you think this quadrilateral that I have drawn here and this pentagon that I have drawn here are convex or not? They are convex because, of course, it is intuitive. If you really want, you have to prove it in higher mathematics. But let us try trust on our intuition. So it means that any pair of points that any pair, or I would say every pair of points that you choose interior to this shape and join them with a line segment, the whole part of the line segment lies interior to the shape. Yes? So that is intuitively clear that this pentagon that I have drawn is actually a convex pentagon. Okay? And then we can also think about quadrilaterals, pentagons, I don't know, n-gons in general, that are not convex. For example, let us consider a non-convex or a concave quadrilateral. So for example, I can have this situation. One, let me make it better. So this is not good yet. 1, 2, 3, so let me just draw this more, and hopefully I can connect this to that. Yes, something like that. If I ask you what is in front of you right now, even though it might look unfamiliar, but that is also a quadrilateral. because it consists of 4 line segments, yes, and it is closed. And then you see what is the main difference between this quadrilateral that I have drawn here and this one. The previous one is convex, this one is not convex, yes? Agree with me that is not convex, yes? Because, for example, if I take this point and that point, of course there are many pairs, there are infinitely many pairs that if I choose and join them, all the line segments will lie inside. But at least I can find a counterexample like this. So this quadrilateral is not convex. Okay, now I want to talk a little bit about what happens for the sum of the interior angles of this one. And by the way, the notion of interior and exterior is not a simple matter now, yes? So, by the way, here intuitively we understand which part is the interior and which part is the exterior, yes? Okay, now let me ask you, what is the sum of the interior angles of this quadrilateral? I want to see, is there any difference? Because if I ask you this question for this, you immediately hopefully answer. That is what? 360 degrees. Let us see that. Is there any difference if I make it a non-convex quadrilateral and still ask you the same question? So this angle, let me call it A. This angle, let me call it B. This angle, let me call it C. And hopefully you agree with me which angle I should call D. Yes, this bigger angle. Yes. These are angles interior to this quadrilateral. What is the sum of these? Yes?
360.
It's again 360 degrees. It's not that easy, by the way, because when it comes to non-convex polygons, we have a lot of degrees of freedom. How to draw them, I will tell you right now a little bit. I want to feel it a little bit. Yes, I don't want to delve into it that much. But I hope that you agree with me. We can prove it very simply. Yes. So what's the proof? Exactly as before. For example, I take this one and connect it. For example, I can take this one. This is better here. I can take this one and connect it here. Yes. And then I will partition this into 2 triangles. Hopefully you can see them, yes? And then this part plus this part plus this part is 180. And this part plus this part and plus that part is also 180. So what happens, if I add them, it means that I have considered all the angles. Is that understandable? So, okay. So it means that that's again 360 degrees. Yes, but proving this in general is not that easy. You need to change your method, yes, because there are many ways that I can draw this. Let me just tell you one more. Okay, so here, let me see if I can draw it better. So let me work with it. Well, let me just check it once more for a pentagon. So for example, here what we have this. Yes, that is also a pentagon. 1, 2, 3, 4, 5. Okay, so what is the sum of the interior angles here? In the normal pentagon, according to this formula, if I plug 5 here, I will get 540. So 540 is the sum of the interior angles of this pentagon, which was a convex one. But this is also a pentagon, but which is not convex. Okay, let us try at least to check. Yes, and I want it to feel something after this. Okay, so let me call this angle A, this angle B, this angle C, this angle D, and again this interior angle E. And I want to prove that the same is true for this one. Okay, so what happens this time? For example, I can take this E and connect it here and there. Yes. Then how many triangles are involved? 3 triangles in this particular shape at least. Yes. So, and then the sum of these 3, the sum of this and that is 180. The sum of this and that is 180. And the sum of these 3 are also 180. Yes. So if I start adding them up, it becomes 540. Yes.
So if you make that shape, but with two perfect triangles, so like, if there wasn't like an extra, oh wait, I mean, oh no wait, sorry, I forgot.
Okay.
I forgot.
Okay, but now the interesting part comes in when I drag this a little bit more so that it crosses over this line. Okay, that is probably not intuitively a pentagon, but according to definition, it's a pentagon again. So be careful about this. You see, I want to take this one, assume that these are rubber bands and these are nails, but this one I detach it from the board, stretch it a little bit, and then press the needle here. Then I will get another shape like this. So if I cannot exactly copy that, but you understand what I mean. So for example, let me just do this. Something like this. Yes. So how many straight line segments you see? Again, 5. 1, 2, 3, 4, and 5. Yes. So that is also a pentagon. Yes, it consists of 4 line segments. And of course, is it convex or concave? It's not that easy to understand it from abstract point of view, because you need to know the interior now. Yes? Of course, you might say that this is not convex. Intuitively, you might think this is interior, this is interior. Okay? But we need to have a good definition of what is an interior. So if I just draw a closed curve here for you, every one of you understands intuitively that, okay, this part is the interior, what is outside is the interior and the curve itself. And that, by the way, that's called Jordan curve lemma. So Jordan lemma. So in advanced mathematics, it's a very hard problem to prove that every closed curve in a particular space actually partitions this space into 3 parts: inside, on the rim, outside. Even though it is very trivial, but proving it mathematically is not that easy. So let us take this for granted, that we just rely on our intuitions and we are not dealing with very abstract artificial spaces. We're just working in this normal universe, Euclidean geometry. So, but now, if I ask you, how can you answer the simple question here? Where is the interior of this? Can we somehow define the interior of that? The interior of this is still clear. Yes? How can I define the interior of that one? How can I give the idea? How can I define the interior of that? Yes? Do you want to say something?
I have heard about the definition that says that if we consider any point, it is then we can shoot a ray or trace a ray out from that point in any direction, and if it intersects with our shape an even number of times, then we know that we are on the outside, and if it's an even number of times, then we know that we are on the inside.
So this is more or less correct, because so you are here, if you are in the interior, yes, and then in any direction you send out a ray, yes. Yes, so this is the intersection could be only one time. This is odd number, and then might be if you are here, and then if you consider this one, you have 2 intersections, which is an even number, and you're outside. Yes, but a little bit simpler than that for this case. Yes, is that if I start moving on the rim in the counterclockwise direction, yes, this is the definition that I want to adopt here. If I go counterclockwise on the rim, the interior always lies on my left-hand side. Yes? So you assume that this is the top view, and you see that I am moving from the top on this rim counterclockwise, And in this intuitively clear picture for me, I see that all the time the interior lies on my left-hand side. That's also one simple way of defining the interior. Yes? So here, when I go here, so I just want you to understand the interior angles. So which one? For example, in this case, this seems to be the interior angle. So I start from here and I start moving around. Yes. So what happens? So when I move around, the left-hand side will be here, and then when I move around this one. So these are. So I want to talk about interior angles. So what are the interior angles? The angles that lie always on my left-hand side. So if I start moving here, this angle is my point, and then when I come here and move in this direction, this angle would be the interior angle. When I come here, so be careful, these are my knots. When I reach here and I want to turn over, this is my left-hand side angle. When I reach here and turn over, this will be here. And be careful, which one is the interior angle now?
The one that looks exterior?
Yeah, the one that looks exterior. So when you go here, so this would be E. Yes? So and so this is of course intuitively clear because I intentionally drew this one for you. So if I bring it closer and closer here, you don't have any doubts that still that angle is the interior angle. Yes? I don't know in which way you want to convince yourself, but this is the interior angle, which seems a little bit odd, yes? Might be in the beginning you might say that this is the interior angle, but according to this, this is the interior angle. But let us check for this one. Is AB plus C plus D plus this E is still 540? Just case by case, because you see, I want you to understand, the freedom of drawing is tremendous. There are many ways, even you cannot imagine how we can consider all cases, yes? Because I have a lot of degrees of freedom when it comes to non-convex polygons, yes? But let us check, is this still true that the sum of these 5 angles is 540 again? Do you think it is true or false for this case? When it passes that, of course, it doesn't matter. Hopefully you agree that if I put this one here, it is still true. If I put it here, it's still true. But what happens is something interesting happens if I cross this border or not. Still, A plus B plus C plus D is plus E is 540. Is the question clear? I just want to give you a flavor of the hard part. It's not that easy, okay? To consider all cases. And then I want to give you a very nice theorem without proof. If you want, you can also do some research about that. And you can also think about your gymnasiearbete from now, okay? If you have some topic, you can just start working on it, and then in the 3rd year, you are more or less relieved, okay? So that's one of the good topics that you can think about. Classifying curves on the plane, yes? Okay, so let us check it in just for this particular case. Proving things hard is probably, proving things in general is very hard. Okay, so how can I prove it? Or at least I want to see if it is true, because I cannot say prove because still I don't know if it is true or false. I want to add A plus B plus C plus D plus that E to see if this is still 540. Do you have any idea how to do that? So we want to calculate A plus B plus C plus D plus E. So if you don't mind, let me give you a little bit of time, because this I'm sure that you can do it. Just let me give you a little bit of time. Okay, did it work?
Yeah.
Okay, so for example, what can you say? How do you want to go?
We could.
I can give them names if you are more comfortable. A, B, let me just take them. A, B, C, D, and E. These are the vertices of my pentagon. But let me just, for simplicity, give some names for X and Y. Okay, let me take the knots from them. So these are not the vertices of my pentagon. Just put it for reference. I just gave them names. Yes.
Wait, so X and Y, are they the name of the points or
the name of the points?
The name of the points, okay. Well then, I define the angles alpha and beta, which lie on the points X and Y within the section
so
points.
here you say alpha.
On the inside of the shape.
Yeah.
Or
this is alpha.
there, yeah.
And this is probably beta.
Yeah.
Yes. Yes, and then.
And then we can also define the point E, but on the opposite side, so the remaining angle, gamma.
E?
No, gamma.
Yeah. Better, yes.
So, firstly, we can say that alpha and beta are equal to 180 minus A and B, and 180 degrees minus D and C, respectively.
Yes. So you say that alpha is 180 in this triangle you are working now.
Yeah.
Alpha is 180 minus the sum of these two angles. Yes. So let me write 180 minus A minus B, and then you can write the same thing for beta in this triangle. So it is 180 minus D minus C minus D. Let us keep the order. Minus C minus D. Is that understandable for everyone? So I'm just working. Okay. And then
we can also define gamma as 180 minus
360.
A minus alpha minus B.
Why? Because if this is alpha, this is also alpha. If this is beta, this is also beta. Yes? And then it means that gamma is equal to 180 minus alpha minus beta. That's also correct. Then?
And now we can say that if we let's see, the way I did it was I just made a new variable called S, which I define as the sum of the angles, and say we know that S should be equal to A plus B plus C plus D plus E.
Where is that angle?
No, that's just the sum of the angles.
Okay, so
I just was temporary, just have something to write on.
Okay, what should S?
Yeah, is equal to A plus B plus C plus D plus E.
Okay, so you are giving this sum a name.
Yeah, just
A
to
plus
have
B
something.
plus C plus D without E.
No, with E.
With E. Okay, so that's the question.
Really, I don't need it. We could just not write
no
this.
worries. You want to find the sum.
And now we could recognize that E is in fact equal to 360 degrees minus gamma.
Minus gamma.
Because
because the whole thing is the whole plane. Yes?
Yeah.
Exactly. And
then if we substitute in the value for gamma and the values for alpha and beta,
yes.
All the A plus B plus C plus D cancel each other out.
Yes.
And we're left with 540 degrees.
Yes.
So.
Yeah, that works actually. That's not wrong. But let me see. This one is the sum of those two. And that one is the sum of those two. Okay, that definitely will work. Yes.
Well, I had a different. Well, it's very similar, but
yeah, because this. Yeah. Okay. So let me just see. What do you say? Do you want to keep these?
No, I want to keep the angles.
Okay. I will keep the angles.
So yeah, I did kind of the same thing, but instead of writing alpha as 180 minus A plus B minus B, I wrote A plus B as alpha as 180 minus alpha. Okay, so the entire solution was I replaced A plus B with 180 minus alpha. I replaced C plus D with 180 minus beta, and
so you started from the sum.
Yeah, I started from the sum.
Okay, that's also good. So you say that the question mark instead of A plus B,
yes,
you write what? 180
minus alpha.
Minus alpha.
Yes.
Then you can see that which algebra is better, because essentially the concept is the same. So which algebra is simpler for you to do, that's up to you. And then instead of the sum of these two, what do you write? 180 minus beta, and then E is left.
E, so I wrote E as 360 minus gamma.
Is that right?
Yes.
So he started from the question mark like that.
Yes.
Instead of A plus B, he has written this 180 minus alpha, hopefully understandable for everyone.
Yes.
C plus D in this triangle, this one, and instead of E, that one.
And I mean,
that's the same concept,
yes,
but written in this form. And then what do you say?
And then you see that
these two numbers is 720.
And then you find that
minus alpha.
Exactly.
I can take a minus sign out.
Yes. So that's one.
So this algebra might be a little bit simpler. Yes.
Oh yeah.
So that is, so sometimes, of course, sometimes it is good to think in that way because there are different ways of thinking. So you have started from the sum that you want to do and try to see if you can do something like that. But you have already discovered the patterns and they want to add up to do that one. It's up to you. I think this algebra is simpler, isn't it? So that's up to you. But anyway, we're still, in both ways, we confirm that still it is 540, yes? Okay, let me also tell you something a little bit deeper without proof, and then we can carry on. So there is a very nice idea in geometry about these things. So for example, let us consider this quadrilateral. Okay. So you want to find the sum of the interior angles. Of course, that was very simple, we could do it, but I want to change the perspective. That is a very hard step to do in mathematics. To change the perspective in a way that I can solve this problem together with the non-convex problems in the same way. Yes? So this is a very hard thing to do in mathematics, and sometimes you have to be very, very smart to discover that, okay? So here you see, the way that we do it, we replace it by a little bit of curved shape in the way, so something like this. Instead of this line segment, consider a little bit curved, bent line segment. And then I want to make these corners a little bit small. You don't have to do that when you learn what I mean. So instead of that one, I will have smoothly make it like this, and then smoothly make it like this, smoothly, okay? And then we go here, and then we do this. A very smooth shape. So assume that these are rubber bands. I am not tearing them up. I'm just deforming them. This is one part of mathematics called topology. Yes. So in topology, we are somehow related with geometry, but geometry cares about lengths and distances. But here we just care about continuity. If continuity is not changed, that and that in topology are the same shape. Yes? Okay, and then what I say is this. Start from a point here. Just imagine a direction. So for example, I don't know, it's a little bit hard, but let me just draw perpendicular to this. Perpendicular. So this is one point that this vector is pointing in that direction. Then I start moving around this circular, this object. Okay, and count the number of times that this arrow will point exactly in the same direction. Okay, so if I start going around, so you see this is a little bit tilted. Yes, it is not the same. If I go around and around and I keep this perpendicular to that, it's not in the same direction, it's in the opposite direction. So when I come back, I will reach exactly here. So how many points I found for having this vector in this direction?
One.
Just one. This I call it K. K is 1. Okay? And then you write this formula. Do you remember this formula?
Mm-hmm.
But now this formula is very interesting. It becomes 2 times K. Okay? It's a very interesting problem. So here, so what is K in this problem? It is 1. And what is N? It is 4. So in this problem, N is 4, K is 1. Yes? And then if I plug these numbers into this, it becomes 4 minus 2, 2 times 180, 360 confirmed. Is that understandable? Yes?
So, like in the case of the normal quadrilateral, that like you don't have to count every individual time it passes over like one of the sides, right?
No, that's what I'm saying. That's what I'm saying. If you understand what's going on, you have to count all of them the same.
Yeah.
So all these line segments are identified with one single point. If the arrow is pointing, so that's why I try to make it curve, because what Oscar says is completely irrelevant, because if I take this point in this direction, of course, all infinitely many points here, this will point in that direction. I don't want to have that. But if you understand what is going on, you can identify this line segment with one single point. So you don't count them infinitely many times, you count them only one time, yes? Okay, so that is why I made it a curve, but of course you really don't need to do that. So that is a very nice theorem. Let us check it here for the case in which we have this situation, yes? Can you feel from topological point of view, this shape and this shape are the same? Is that understandable? This shape, quadrilateral, that I have here, and that shape or topology. Of course, topologically, it's not a very good word, because that's also topologically equivalent to a circle. Yes? So you shouldn't necessarily make it like that. But what I want to say, if you want to follow that rule, so let me just change it with a little bit of curve. Of course, you don't have to do that if you understand what is the meaning of identifying all those points with one single point. But let us make it a little bit easier for the first times at least. And then I go here, and then smoothly I go here, and then I smoothly go here. Something like that. It's probably, I can do better. Yes, something like that. This is very bad. This should be no interruption here. Okay. Now, what is your guess about the sum of the interior angles here? If I take one vector here, and I start moving around, in how many points I will reach exactly the same direction?
Only one.
Only one.
Yeah.
So that's the answer again, 360. So that was a very nice property, the person who discovered that, okay? So let us also check it for this one. Let us check it for this one. Yes? Let me check it, by the way. Let me check it for this star. Yes? So what was your prediction? It was 180. So let us see if it works here or not. Okay? So, what is n in this problem? What is n in this problem? The number of sides. What is the number of sides? What's the number of sides here?
What?
The number of sides.
Sides.
5, yes?
Yeah.
1, 2, 3, 4, 5. So n is 5. I need to count k. So what is k in this case?
2.
Is it 2?
It's 2.
Did you confirm that this is 2? So I don't know if you understand what it means. So let me just draw one perpendicular vector here. But when I start moving around, don't count them, because still they are on the same line segment. All of them should be counted once. Okay, now you see, assume that I am just rotating around. So you see that all these vectors are pointing in different directions. So I shouldn't count yet anything. And then I go back here. I don't need to count. I go here. And then I will go back here. Yes, still no counting. A counting will happen here. Do you agree?
Yes.
So one time. Yes? Another time he's there. Then if I continue back to the same point that I started with, nothing will match again. So k is 2. Is that understandable? So k is 2. And put it in your formula now. N is 5 minus 4. Yes? multiplied by 180. It's 180. It's a very, very nice property and exciting, I think. And I don't have any clue how they want to prove it in general case. I haven't seen that, to be honest. But it's a very nice property. Yeah, I think you can also do some research, and if you have something, you can come here and present it. I think it's a very nice topic. It's completely generic. So can you just see what happens here? Let's just try it once more, and then we can move on. So I start from here. So first of all, how many sides are involved here? Again, 5. 1, 2, 3, 4, and 5. So I start from here. I rotate, no matches yet. I go here, rotate, no matches. I go here, and then I rotate, one more match. Agree? Yes?
What?
So you, by the way, you really don't need to be worried about exactly, because if that match doesn't happen here, it will definitely happen somewhere else.
Yeah. But,
Yes? So that's the point. I don't know exactly the numbers, but how much was the match? Was it how much?
twice, but that.
No, but this doesn't work then.
Yeah, it does. I mean, should like.
So let me see.
Doesn't the shape have to be like convex for this to work?
No, that's the whole point.
Or-
That's the whole point. If I understood it correctly.
Or because we're like talking about topology.
No. But
This-
let me double check again. So you start from here. So no matches definitely.
Mm-hmm.
We'll go on here. No matches here. Yes? And then we go here. And then I will start rotating up to here. Okay?
Yeah.
Might be in this shape, there are no matches yet.
Yeah.
And then will I come here? Then what I have to do? I have to rotate about the other side, yes?
Yeah, to the right.
Yes. I have to rotate to the right this time, no.
Um, you have
Let me
to
see.
go-
So let me see. So no matches actually happens.
Yeah.
Yes, because you have to rotate back again.
Well, yeah.
And then you go back here. So there's
But-
only one point.
But like, if we put E further down, then we could definitely have like a match.
Can we?
Yeah, because then the slope of E and D could be greater than the slope of A and B, and then we would definitely like
No,
have.
if
No, apparently if that's correct, this is not going to happen. Because otherwise we're violating that
Yeah.
theorem, yes?
Mm.
But in this case, in this case we have also one match, and that happens here,
Mm,
yes?
Yeah.
So let us think about what you are saying is that, so you mean that if I start moving this around
Mm-hmm.
in this direction, or
Oh,
so if
yeah.
I move it around, what will happen?
Well, if we make the triangle, the top two triangles exactly the same, they should be a match, right?
So let us make that. So what you are saying is that let me make it exactly the same triangle. Yes?
They're
Yeah, let me
perpendicular.
make all of the triangles the same if you want to.
The perpendicular should be the same, right?
Yes.
So there should be a match. If-
So it means that you are saying that, okay, I will take this one parallel to this one.
yeah.
Yes.
You should find that they are a match.
And then you are right. There will be another match when I go there. Yes.
Yes.
Like,
So might be that is related to the direction of rotation as well.
because in like, or are we allowed to make intersections in topology?
Yes, in principle, the interesting. So might be I have to read a little bit more about this and see why you are right. It doesn't work here, because if I make these two like that, then of course, definitely, if I draw these parallel, I will get another match here. And then what was the answer to this problem? It was 540. Yeah. Because the whole point of this theorem, if I remember it correctly, is because even if you have intersection points, it doesn't matter.
Mm-hmm.
Because otherwise this is not very interesting anymore, yes?
Yeah.
So might be I have some conditions in that theorem that I am not aware of, so I have to read it a little bit more to see what happens in this case. But apparently you are right. If I draw these two lines in parallel, and then I will have this one, and if I rotate this one, so it might be I go interior ones, yes? Yeah. Here. But there is something happening odd here, yes? There's something here will happen. And then I will get back here, yes? So anyways, I will have two matches. Okay, let us leave it like this, and I will draw. You can also do some research about it, and to see how this will go. Okay, yeah, let us keep this one. This is very interesting question. So that was good that I checked this one as well. Okay, but now let us talk about the other two cases that we are left from the previous session. But these kinds of theorems are actually very nice. So you see that you are changing your perspective to be able to contain very special cases, all more or less all cases, considering combining the convex problems and non-convex problems into one problem, if you understand it correctly. It might be in this theorem. You are not allowed to self-intersect, but of course it worked for the case of the star, but it might happen that that's just a coincidence. Okay, so let us see. There was another problem, if you remember. We can also check it here, by the way, that's interesting. So we had something like that, if you remember. We started from something similar to this shape. Yes, something like that. And if I remember, I named them in this way: A, B, C, D, and E, F, and G. Yes. And then we want to answer the same question. We want to add these angles: A, B, C, D, E, F, and G. We want to find a sum. This was also one of the exercises that we have 2 sessions back. Okay, so do you have any ideas here? But first, if you don't mind, let us check it using this method to predict what will happen. For example, let me start from here, this direction. Then I go, and here, no matches yet, no matches yet. But here, when I turn around, no matches yet, probably, but apparently when I turn somewhere in between, I have one match. And then I will go back here, then here, no matches anymore. So if I understood it correctly, there are 2 matches here. One occurs at this point, and one occurs when I am passing through this point. So it will be 2 matches. So what are the number of sides? 1, 2, 3, 4, 5, 6, 7. So then n is 7, and k is 2, and if I plug them in the number, in the formula, so it is 7 times minus 2 times 2. So it should be 540. I don't know, have you solved this problem? What was the answer?
540.
Was it 540? Okay, so it works here as well. But that is a very nice example that it doesn't work or we understand it wrong. Okay. But let us forget about this formula. I will try to study a little bit more. It might be I have forgotten the details. I just try to say you something from my memory. Okay, so now, so what about this one? Can you prove it?
Yes.
So how should I do that?
Well, I'm looking. Okay, I can say, but I feel like I found a flaw in my proof. But okay, I can check it out. Okay, so what I did I considered. Well, the pretty obvious triangle there.
So if you don't mind, let me.
Well, I marked all the angles
them,
first.
yeah, let me give them names.
Yes.
So let me just. These are not dots. These are not vertices. Let me call them X, Y, and Z if you want to name them.
Yes, and well, I considered all the interior angles, so like the quadrilateral and the middle.
These ones you mean.
Yeah, these.
Alpha, beta, gamma, and E.
Yeah. So what I did was that I found that like the sum of the angles is there's the triangle there, and then the one I don't want is gamma, right?
Yes.
Then I found to the right that you can draw a quadrilateral that like makes X, E, F, and G a quadrilateral, and I don't want alpha.
Okay, so you mean that you actually started writing things out, yes?
Yes, I considered all the shapes I wanted the sum of the angles of, and then I removed all the angles I didn't want, and I found
Okay,
that
I understand.
those
So you
angles
did
together.
some gymnastic with the numbers, yes, with the
Yeah.
letters and things like that. So let us see if there is there any other suggestions? Any one of you others? No?
Det var väldigt konstigt.
Vänta, jag var räknade ut fel till 2540.
If I have done it myself, I don't remember.
Alltså, jag gjorde ju någon magi här med slängde ut massa grejer på. Men
För jag sitter ett film för den här, det vill jag ha.
So for example, I started like this, I think, if I remember it correctly myself. I want to have A, B plus C involved, and this is a quadrilateral. So I call this angle probably something, let me call it alpha. And then what I do, I would say that, okay, A plus B plus C plus alpha is 360 degrees. And the good point is that alpha is an exterior angle for this triangle. It makes D involved. So alpha itself is D plus this angle, yes? Let me call this beta. So instead of this one, I would write A plus B plus C. So let me write plus C plus, instead of alpha, I put D plus beta. A, B, C, D. I need more, yes? So I have to go for, write something for beta. And I think what I can do, beta is an exterior angle for this triangle. So I just drew this one. So beta itself is this part. Let me call it 1, 2, 1, 2, yes? So if I ask you what is beta itself, so it becomes A plus B plus C plus D. Beta is the exterior angle for this triangle, yes? So it is equal to E1 plus G1, yes? And then the leftovers are E2, G2, and F, which is 180. Yes? On the other hand, we have E2 plus G2 plus F is 180. So this one is 360 degrees. This one is 180 degrees. And if I add these, then I will get my angles.
yeah.
Yes? That's also one way. This is the way that I think I did it, because I see that I have drawn a dotted line there, so might be that was the reason. I don't know. This is the way that I did it. And I don't know what is your algebra. Is the algebra more complicated or simpler? So that's up to you.
Definitely more complicated.
Okay. So what I did, I drew this one. So I started from this quadrilateral, and then I used the exterior angle theorem 2 times. Yes? So then this becomes one. Is that understandable? What I have done is valid, yes? Okay. And then if you remember, there was one more left. It's still interesting. It's bothering me. Okay. So let me, if I could draw the other one as well. We had this, yes? We had this shape somehow. Yeah, and I told that something like that. That's not exactly the shape. I cannot just reproduce it again exactly. But this is A, this is B, this is C, this is D, this is E, this is F, and this is G. Again, you want to answer the same question. What is A plus B plus C plus D plus E plus F plus G? Yes? We want to add them. Yes. So if you don't mind, let us check this method to see if it works, and then you, because you have the answer, we can compare them. First of all, what is n in this problem? N is still 7, yes?
7.
And what is k? Because I have 7 sides. And then what is k? Let us check. For example, I draw this one and I start rotating. No matches yet. No matches yet. So here, no matches yet. But hopefully you agree that there definitely will have a match here. It doesn't matter if I know the angles or not, but definitely when I'm passing here, I will have one match. And then hopefully you agree there will be no matches. So that still k is 2, and then the numbers is still should be 540. Is it true or not? What did you get for this?
Yeah, it's 500.
540. So we have to really see that why it doesn't work for that case. That was a very nice thing. Yes.
Maybe one thing that I just thought about and why it doesn't work in that case. Maybe it's only when you can guarantee know that it's always that it's going to be a match. Because in that case, in one specific shape, you can find that if it's parallel, you will find. But if it's always guaranteed to be in any given shape, that it's always going to be matched at a specific point, maybe that's the case.
Yeah, that might be. I understand what you mean. Yes, so it should be independent of the details, but that is not a very good mathematical theorem because you want something to rely on always. Yes, in that case, might be I have to reconsider. I really don't know because I remembered I read something about it, and it was probably for me that at that point obvious, and for some reason I didn't have that particular example in my mind to check. And that is very good that we did it today. So I see that. But something strange happens here because the rotation, the direction of rotation changes at some point. You know, here I am going clockwise, counterclockwise. Yes, and when I reach to here, I suddenly go clockwise.
Yeah, wait, shouldn't it be like that every clock or something where you instead should like add or subtract turns?
Yes, that I remember. This happens, but then it doesn't. So it doesn't matter the matches. Yes.
Oh yeah, or shouldn't be like, or do we add one?
Yeah, might be that is more deeper. It depends the direction of rotation as well, because this is the only difference. That in the normal one, we don't have this scenario, have we? If we have this. Yes? Is it the same still? We go here, counterclockwise, counterclockwise, counterclockwise. No, it's still we have.
Yeah, because we probably we add one turn when we go down into the valley.
Yes.
But then that turn gets undone because we rotate the other way.
Yeah.
But like how you...
But this is also somehow undone, partially, yes?
Yeah.
So every time it changes direction, one is undone.
No, might be I am just confusing myself. So might be we should always point to exterior. So, okay, so that is the internal angle, yes? Okay, let us think about it because we will spend. So I'm not sure. Let me just think and read a little bit more about this. Become more confident next time. Okay. Okay. So now, so let us talk about this one. I don't know what is your scenario to calculate the sum of these angles, which in case it works here as well.
This was probably the easiest one. You just see that.
Yeah, I think it's the easiest one. Yes, isn't it?
There's a pentagon on top, and you find that the exterior angles of the triangles. Make up for it.
So what where do you want to start from?
Okay, so if you look at the pentagon at the top, the two remaining angles without names.
This one?
Yes.
Okay, so I will give this a name, alpha, and give one a beta.
Yeah, and you find that
the sum of these...
Alpha is an exterior angle of, the right triangle.
This one, yes.
And then beta is
the exterior of this one.
Yeah,
and then we are done. Yeah, that's probably simpler. And that's, so let me just... So what we know in this pentagon, that A plus B plus alpha plus beta plus G is what? We know that by now. Is that what? Yes. And then you are right. This alpha that you have here plays the role of exterior angle for this triangle. Yes? Can you see that? So this alpha should be C plus D. So this alpha can be replaced with C plus D. And similarly, beta is an exterior angle for this triangle. Yes? And it is E plus F. So instead of beta, you can put E plus F, and then you also have G. So you have all 7 angles that you need, and this is still 540. So we actually discovered something which I was a little bit careless about when I was training you. So it means that there is one thing different for this and that one, and then this one is that we actually change the rotation of that vector, the direction of rotation, clockwise, counterclockwise. But in all of these other cases, we are sticking to the same direction of rotation, yes? So that is probably the reason that we have to modify this a little bit.
Möbius band.
Okay. Yeah, we can read together. If you're interested, we can read and discuss about this later. Okay, before, I don't know how much time we have. If you don't mind, I want to write a question for you so that you can solve it for the next time. And if you have more time, there are some simple problems that I can design. And then we carry on to the next very interesting topic after that. So the next topic will not be related to angles anymore. We just move on, okay? So this one I want to write down formally, and I want you to think about it for the next time. So let me write it officially in words, and then because also drawing somehow appropriate picture for this, or image, or figure is probably a little bit challenging itself. So given, let me write it for you here, given, and please write it down and try to think about it in one reading. Given a quadrilateral ABCD, and I told you that when you write a quadrilateral ABCD, you have to keep the order. You cannot just go zigzag, yes? So you start from here, A. So you have to name it A, B, C, D. When I say A, B, C, D, that's convention. A and C are opposite, B and D are opposite. So given a quadrilateral ABCD, E is a point on E, on AD, if F is a point. By the way, from now on, when I don't say which type of quadrilateral, I always mean convex by default. Yes? That's also standard. If they want to say non-convex, they have to mention it. Okay? So if F is a point interior to ABCD, such that this drawing an appropriate figure is a little bit challenging itself, such that CF, you don't need to be precise, but you need to draw something that you can work with it, such that CF bisects this angle, angle ACB. I am using a standard convention, so C is the vertex, the middle one, and EF bisects angle BED. Prove that if this is happening, prove that there is no guarantee that in any quadrilateral this happens, but in a particular quadrilateral with these properties, if it happens, prove that the measure of this angle is 90 degrees plus the average between these two angles. So I want to make sure that I haven't done something wrong. A, B, C, D. E is a point on AD. F is a point interior to A such that CF bisects ACB and EF bisects BED. Prove that CFE is 90, CAD, CB. Apparently, I wrote it correctly.
But
Yes?
didn't we do something very similar to this?
No, it's not very similar to this.
No, the last time we did something that was kind of like this, didn't we?
No, no, no. It was not related to quadrilateral.
No,
And then you will find this question a little bit challenging. When I read it and I wanted to do it myself, I had to draw several quadrilaterals, changing the shape a little bit so that it seems reasonable what is written here. Yes? This is not claiming that in any quadrilateral you have this, but in a quadrilateral, if this happens, we're supposed to prove that this will also happen. Yes? Okay, so let me ask you one question. Can you solve it immediately? I want to test you, see how you can find the relations quickly now, because now you have a lot of experience now, and then you are supposed to use it somehow to do this. So let me just tell you something. We have a little bit of time. Might be that would be our last problem today. So I have an isosceles triangle here, ABC. Isosceles here, I mean AB is equal to AC. And we also know that there is a point D here. Yes? That might be here, somewhere here. So that CD is also equal to these. Yes? So AB is equal to AC in an isosceles triangle. D is chosen in a way that from D to C is also equal to these two sides.
Right.
Yes? Yeah. And then you connect this one to this one. And then from D, you draw a perpendicular to AB. Yes? And then what I am asking you to find, I give you this angle to be X, this angle to be Y. I want you to find the connection, the relation between X and Y. Yes? So what is given here, AB is equal to AC is equal to CD. I drop a perpendicular line from D to A, and this angle is X, this angle is Y. I want you to find the relation between X and Y. Yes? In principle, you should be able to manage it in 5 minutes. Of course, I don't want to give you stress, but you should be able to do that. Otherwise, we keep it for the next time as well. But this problem is harder than that one. So you need to have to do a little bit of challenge here. Okay, I pause recording to give you a little bit of time to think. Okay, so what happened? I don't want to disappoint you. This is from the exam, from Iranian actually entrance exam for universities, and you have at most 90 seconds. But of course you had the options there. I didn't give you the options, I don't remember them. But what I want to see, it is manageable. I don't know why you didn't do that in 90 seconds. So you didn't take my advice seriously. Can you tell me what should I do? Have you drowned yourself with letters and things like that? I told you not to do that, yes? So when this is Y, this is also Y.
Yeah.
Yes or no?
Yeah.
Yes.
So then what is this one? And what is this one? They are equal.
Yes.
Because I told you that AC is CD. So if this one is equal to that one, this angle and that angle should be the same.
Yeah.
So what is that one? What is this one? Can you tell me?
It should y divided by 2 minus 90 degrees.
The other way around. 90 degrees minus 1 over y over 2.
Okay.
Yes or no? Because
No.
the sum of all of them should be 180. So then 180 minus y divided by 2, it's 90 minus y over 2.
Yes.
So that's 90 minus y over 2. Yes?
Yes.
And then what is this one now?
Oh, it's actually 90 minus 5.
90 minus y.
Oh.
And then the relation is found. The sum of these is 180. Yeah, so it is possible to really to do it in 90 seconds. Yes. So because 90, and there is a nice relation, I think it should be this one plus x plus 90 minus y over 2 is what? 180. And the algebra is also simple because 90, 90, 180, they are gone. and then I move these two to the other side. So x becomes y plus y over 2. So this becomes 3y over 2. So that's the relation. I don't know, depending on which way they have given the options, you can choose something.
Yeah.
So it means that if you want to make it nicer, 2 times x is 3 times y. Yes? So 2 times this angle is 3 times larger than this angle. So that was the relation.
Yeah.
Okay, so I want you to train yourself. I know that I have to sit down and write a lot of questions for you so that you can practice. But unfortunately in geometry it is not just typing. You have to draw many shapes and things, and it is really time consuming. But at some point I will do that, okay? Okay, so let me just stop here. Next time, I will not continue with angles. Of course, every now and then I will give you some questions related to angles so that you can practice more. But I will move on to the next interesting topic, which is the congruency. By the way, Math 2C, you will also learn that. Congruency of triangles and things like that. So it would be completion to that part as well. Okay, any questions? Okay, we can together read a little bit about what happened in that problem, yes. Yeah, we can discuss about it later. Thank you very much.
Thank you.
Any questions you have, Rasmus?
Yeah, about that one.
This one? Yeah, that is a little bit hard to draw, because I remember when I was doing it, I can show my scratch paper, I tried to draw it in a way that it makes sense in the first place so that I can prove it.
I tried to draw it and it doesn't really make sense, or just the angle ACB.
No, I don't remember where I
Oh, wait.
took it from. So you see that I have drawn some shapes here for myself. It didn't work in one of them. It was completely strange that it is not true. But then I try to change my shape in a way that it makes sense. What I'm saying is that it is not in all quadrilaterals. There is a quadrilateral with that property. In that one, we are supposed to prove this. But of course, you need a figure to start with. Yes?
But shouldn't this be general? Because we just defined that it should be any quadrilateral.
No, might be.
ABCD and
No. Yes, might be they are not very careful in designing the question, because not in all quadrilateral this property works. You can just draw a shape and see that. No, let us. If I have written it wrong, because I've just copied and pasted from a book. I think I don't remember exactly which book. But the point is that if I have a quadrilateral which enjoys these properties, then prove it there. You can imagine it in that way. Yes?
Okay, sure.
Yeah. Thank you very much.
And when you think of angles, you go counterclockwise.
No, it does.
Or how do
Yes,
you find which side it's on?
I don't think none of them will be relevant here if you're working with a convex, a quadrilateral here. But the important thing is that the number here in the middle is the. So of course you are right. So in principle, what I mean is that if I have this A, C, B, this is what I mean here.
Yeah.
Yes, it doesn't matter. So if I read it in that way, I understand what you mean, because in principle direction matters. In other case, you can go the other way around. Yes.
Mm.
Yeah. But let me take the angle between 0 and 180 degrees. So let us consider this one is referring to an angle between 0 and 180 degrees.
Okay.
In that case, you don't need to be worried about this part.
Yeah.
Yes.
Okay.
Thank you very much now.
So